right. So if you took 10 million of these, you'd go from the North Pole to the equator. So they used the Earth to make the meter stick. Fine. Then they did something nobody else had ever done. I'm going to use this stick to make a container for volume. This is great for measuring distances, kilometer, micrometer. See, I got all the distances down. I just have to use some prefixes. Did they use French words there? No. They used Latin and Greek, didn't they? Every language in Europe was based on Latin, wasn't it? Latin and Greek. Okay, so now what? We're going to make a box. How about, hey, let's make it 1 meter long. That'd be easy. 1 meter wide, 1 meter high. What do you think? Huh? Nice box? Would you use that box?
No.
That's huge. It's huge. You couldn't even carry it. If you put water in it, nobody can carry it. So what's the next choice if you can't make it this big?
Chop it off.
How many pieces?
10.
Don't say 8, 10. So what's 1/10? What's 1/10 of a meter? That's called a decimeter, isn't it? Isn't 1/10 of a meter the same as a decimeter? Is that right? Notice how as the unit gets smaller, the number gets what?
Bigger.
By powers of 10, doesn't it? So anyway, all I know is I know my powers of 10. I know this thing is 1/10 of a meter long and 1/10 of a meter wide and 1/10 of a meter high. That's how they made that box. And they made that. That's why the liter is not in the SI system, because it can be defined in terms of the meter stick. Get it? I don't need a separate one for liter. Now, we talked about this yesterday, and I think we finished this chart yesterday in your class, didn't we? As long as you know that, you know length times width times height. Give me the rest of these now. This box could be called 1 liter. It could also be called what?
100.
1,000. 1,000th of a...
Meter square.
What's meter to the third power also called? Meter cubed. What's also called? A cubic meter. A cubic meter is a meter to the third power, isn't it? And it's a cube, isn't it? It's a big old cube, isn't it? It's a big one. All right, what else does the volume? What if I used decimeters? 1 decimeter long, 1 decimeter wide, 1 decimeter high. What's that equal? 1 times 1 times 1. Oh, see? That's, you know what a liter is called? A cubic decimeter. This is a cubic decimeter. Okay? Pretty easy? Pretty easy. What's the other one? Give me another one.
Centimeter.
All right, how many?
10.
Times?
10 times 10.
How many is that?
1,000 centimeters cubed.
Right? Is that right? Okay. And I'm going to show you something here. See it right there? That's a cube. It's 1 centimeter long and 1 centimeter wide, 1 centimeter high. What would be a good name for that? Reese, you know. What's a good name for that? It's 1 centimeter long, 1 centimeter wide, 1 centimeter high. It has 90-degree angles. Say it again. It is. This is a cubic centimeter. But wait, you said that this box was what? Not one of those, but how many? What? No way. There's no way 1,000 of those would fit in there. Really? How many fit along one side?
100.
How about this side? How about the bottom floor? How many floors? Oh, yeah. This. How many? So the liter box is how many cubic centimeters? Okay, now, what's powers of 10? Watch this now, ready? This right here is 1/10 of this box. What would be a good name for that much volume? Right there. How much volume is that? Somebody said it. What? What? 1/10 of this box. What is it?
Decimeter.
Deci what?
Meter.
What? Say it again.
Decimeter.
No.
Deciliter.
What?
Deciliter.
Yes? Okay. This is a liter. What's this? What's this?
Deciliter.
That's a deciliter of volume. I've never used that word in my life. That's fine. This right here. It takes 100 of those to fill that box. How much volume is this? It's 100th of this box.
Milliliter.
That's 1,000th.
Hectoliter.
What?
Hectoliter.
That's 100. This is 100th.
Thousandth is a
You know, what is it? What's 100th of a liter?
milliliter.
Centiliter. Okay, this is a centiliter of volume. And what is this? It takes 1,000 of these, so it must be what?
Milliliter.
But no, you said it was a cubic centimeter.
But it's the same thing.
That's right. A cubic centimeter is the same as what?
Milliliter.
A milliliter. A cubic centimeter is a milliliter of volume. Everybody got that? Every good science student knows that. We'll do one more, and I don't use this very much, but what if I used 100 millimeters times 100 millimeters times 100 millimeters? What's 10 to the second times 10 to the second times 10 to the second?
1,000 to the sixth.
Wait a minute, let's try this again. What's 10 to the second times 10 to the second times 10 to the second? When you multiply numbers, exponents, you...
10 to the 6.
Now, I don't have, luckily, they did not send me luckily, they did not send me 1,000 cubic millimeters. They're really small, aren't they? But you know how many cubic millimeters would fit in this thing? Oh, you know how many cubic millimeters would fit in here? I'll give you a clue. 10 would go there, and 10 would go here, 100 on the bottom floor, and 10 floors. 1,000 cubic millimeters would fit in this. But 1,000 of those would fit in there. So therefore, how many cubic millimeters would fit in here? 1 million.
A million.
Yeah, 10 to the 6.
All right. Now, are you okay with this?
I mean,
Not really.
This is all about powers of 10, isn't it? All I knew was I knew this box was made 1/10 of a meter long, and I knew my powers of 10. You don't have to go home and memorize these. You should be able to figure them out mathematically, right? If you know that number and you say this times this times this, you can do that. All right, now I want to do one more. I'm going to take you one more place. So this is for distances, and this is for volume, and they didn't stop there. They didn't stop there. Here's what they did. They filled the liter box with a material they thought every human would have to have contact with.
Oxygen.
Gold. You have this much gold?
Yep.
Really? You wouldn't be here if you had this much gold.
I mean,
Now you would be a
Th-
millionaire.
This is a huge amount of money of gold.
Daniel,
So what did they do? They didn't stop here. They said, if you were to fill this with water, okay? Technically, it's 4-degree water. It's cold water. But if you fill it with water, guess what you have? You have 1 kilogram of mass. Oh, no. Are you kidding me? Fill that with water. You'll have the same mass as this guy right here. Not the same volume, the same mass. And they did that on purpose. And what I think is even more neat than this, 1 liter of water is the same as 1,000 milliliters of water, but 1 liter of water is also 1 kilogram of mass. Is that right? Now watch what happens here. A kilogram of mass is also known as what?
1,000 grams.
1,000 grams. Uh-oh, a little algebra here. Divide both sides by 1,000. 1 milliliter of water. They did this on purpose. 1 milliliter of water is a mass of what? 1 gram. They did that on purpose. So what would 25 milliliters of water, what was the mass of 25 milliliters of water be? 25 grams. Did you see how simple they made this? Wow, that's simple. And did one more, and this is on the last page of your chapter. I'll do it now. Does anybody remember density from middle school?
yes. I remember.
Density equals
Mass of volume.
mass over volume. Watch what they did here. What's the mass of this water? 1 gram. What's the volume? What's the density of water? they purposely made the density of water to be what simple number?
One.
1.
One gram.
So if I hear about something that has a density of 5, if it has
we
a,
know him
We know
from
from you.
is he gonna come here?
Yeah.
He was looking at it, yeah.
Okay, good. So if you have a density greater than 1, you tend to sink in water, don't you?
Yes, less.
Because you're 5 times. If you have a density of 5, you're 5 times more dense than the same amount of water. What if you have a density of 0.5?
It's less, so it's gonna float.
Yeah. Okay, everybody got that? So it's kind of neat how they did this. I don't know if I can convince you how simple this is. This system is simple. It's not. You don't think it's simple because they didn't give it to you every year since first grade. Even in the first grade, they talk about inches and feet, don't they? I promise you, if you had this, every third grader can do all these metric problems in France. If I go to France, they can all do those problems. And there's no way if we said by law, in 5 years, everybody can only use a metric system, we would. And you'd be the old fuddy-duddies, and your children, oh, when I was growing up, we didn't have to do that, but you have, you know. But anyway, it could easily be done. England, when do you think England switched over to the metric system?
1924.
What do you think? See, wow, if I go to England now, it's like, man, it's all metric there. And
What's that to do with their money, though?
it was about 1965. And they said, in 5 years, no one can use anything else except a metric system. They gave everybody plenty of time, all the shop owners and things like that. And Canada didn't switch until 1970. And you go to Canada right now, you would not notice it's all metric. United States, the armed forces and sports, track and field, Olympics, they all went to metric before we did even. We haven't even gone completely metric. All right, I'm going to stop that. And questions on that lesson? Yes.
Well, I mean, it's also like really weird when people are saying their height in like other countries. Because you say like 160
Kilograms.
centimeters and stuff like that.
Yeah, but 160 centimeters, I'd probably say 1.6 meters. And then that makes sense to me. If I know what a meter is, then 1.6 meters is about a little 1.5 meter sticks. If I said 1.5 yards, you know how much I'm talking about? So the whole world, if I said 1.5 meters or 1.6 meters, they know what I'm talking about. It's not that hard. How big do you think a kilometer is
Thousands.
compared to a mile?
I mean,
Oh,
less,
more.
It is less.
a lot less.
That's why if you run a 5K, who runs 5Ks in here?
Will.
So how many miles is that?
3.5.
Okay, so a mile must be bigger because there's less of them, isn't there? There's less miles because each mile is bigger than a kilometer, isn't it? Do you know a kilometer is only about 60% of a mile, like 0.6? So if you said, I know what a mile is, I'll go a little more than half a mile, and that's a kilometer. So you can kind of estimate what a kilometer is.
Is that why they're speeding it? Is that why like kilometers are slower than miles per hour?
Not slower. It takes like my speedometer. Okay, I'm glad you brought this up.
Like 100 kilometers.
My 100 kilometers is 60 miles per hour. So it's going to be more kilometers per hour because they're smaller. You're going to cover more kilometers in an hour than you do miles because the kilometers are smaller. So anyway, you can get used to that. It's not if you go to Italy and they start going to Italy again. There's a fraction called 3/5 and 5/3, and or 60% and then reverse that. But if they say it's 100 kilometers, you're going to be on a bus trip for 100 kilometers. You say, whoa, how long is that? Well, 60% of that is had to be 60. It's about 60 miles. So you can, if you're in Europe, then you can simply take 60% or 3/5 of that number, and you'll know how many miles it is. If somebody from over there comes over here and you say it's 10 miles away, and they say, how far is that? Then I multiply it by 3/5, 5/3. That's 50 thirds. What is that?
2.
What was 50 thirds? 16.6?
Yeah.
16.6 kilometers. That's about 17 kilometers, something like that. All right, let's go to another section of the book, okay? one of the sections in the book has to do with this right here, and I'm going to show you a picture here. And again, if you happen to be in my STEM class, just act like you haven't heard this before. But what I'm going to do is I'm going to draw a line, and what I'm going to do is measure it. So I want you to take a look, and here is my ruler. Now my ruler is this here. Does everybody see it? But my ruler doesn't have very many lines on it, does it? It's not a great ruler. It measures in, what metric unit do you think that is? And I'll give you a hint. What is that?
Decameters.
What is it?
Decimeters.
Decimeter. Okay. So this is a decimeter, and there's another one. So let's take a look. And what's hard for me to do is to look at the camera. I'm going to line this up. All right. Now, I want to measure that line in decimeters. So let's take a look. Well, I know it's 1 decimeter, but is it 2? No. I'm actually certain that it's 1 decimeter, but it's not 2. So I'm certain about that number 1, aren't I? But what you have to do in science, when you use any kind of instrument, you have to write down every number you're certain about because of the lines, but then you're forced to guess one number beyond that. I don't have lines past there, but I have to guess. So what do you think? Take a look over there. Do you think that line goes halfway across the next decimeter? Would you say it was 1.5? I don't think so. How about 1.4? No, I don't think so. So what do you think?
1.0.
Okay, wait, let's try it again. See this? I'll try to do this on camera.
Just one guess.
If it went all the way to here, it'd be 2. If it went halfway, it'd be 1.5. 1.4, 1.3, 1.2, 1.1. What do you think? Some of you might say 1.1 decimeters, and some of you might say, no, I really do think it's closer to 1.2. Now what you did, remember I told you every measurement has a number? But not any number. It's the number called significant figures. So every scientist in the world, every engineer in the world knows that when you give me this number here, when you say 1.1 or 1.2 decimeters, you know what everybody who's intelligent knows? I know exactly what that ruler looked like. What? You weren't even there. I know, but you're telling me what the ruler looked like. You're telling me you had a ruler that had 0, 1, 2, 3. You're telling me your ruler looked like that. How did you know that? Because I know that you had to guess in what place. The last number is always a guess, in tenths place. That means you did not have lines for tenths place. See? I don't have lines for tenths place, do I? So by writing this down, I'm communicating with a person how well they can trust that number. Right now, 2 sig figs are not all that trusty. I mean, I wish I had more than that. So let's try it again. I'm going to use a different ruler. What do you think these are? What do you think these things are right here? And I'll give you a clue. Everybody in here, if you turn your little finger on their side, and if you were to line it up with one of these metric rulers, you'd find out that my centimeter is way up here. For some of you, your centimeter is all the way down here. Okay, because my finger is a little bit bigger than yours. But everybody carries a centimeter with them, okay? You should never tell me you can't estimate a centimeter. So I know my centimeter is right there. So I'm going to line this up, and let's see if I can do it on the camera again. All right. Oh, look at this. Look at this. Now, let's do a reading now, and take a look. Is this 10? Is this 10 centimeters? Is that right? Isn't that right?
Yep.
So, oh wait, I'm sure it's 11. I am certain that it's 11 centimeters, and I'm certain it's not 12, right? But what do you think? 11, I have to guess now. When I run out of lines, I have to guess. So what am I going to put now? What do you think? What do you think, Fiona? What would you guess? 5? Things about halfway? Now, some of you might say this, and some of you might say, no, I think I'm okay with that. I'm okay if you said 0.6 or 0.5, right? I definitely think it's definitely halfway, all right? Did anybody say it's 0.4? Okay, now look what happened. With a new ruler, I now have not 2 sig figs, but what? You see that? I have 3 sig figs. Which one of these measurements do you feel better with? This one. Significant failures include all the ones you're certain about because of the lines, plus one guess. One number that's a guess. You get that? Anybody in the whole world, if you're an engineer or a scientist and you wrote that down, I know exactly what your ruler looks like, don't I? What's your ruler look like? I know you have lines for ones place, don't you?
Yep.
In centimeters? And you had to guess tenths place. That's what you're telling me. Okay, and let's do it one more time. This is the hardest one for me to do on a camera, especially when I do it backwards.
You want me to turn the lights off?
Yeah, sure then.
Wait, just turn off the first set here by the wall, not the one by the door. No, the other way. Do this one and not that one.
Oh.
Okay, let's do a little magic here. Ooh, okay. Now, we have a nice ruler here. These are actually in millimeters, but I'm going to use the word centimeters. So, what do you think this one is? 11 point, maybe not quite 5. What do you think?
I think it's 5.
Okay, now, okay, good. I've got good point. Now, I know I'm magnified here. Do you think it's 11.5?
Yeah.
Anybody think it's a little bit less than that?
Yes.
I think it's a little bit less, but that's all right. So let's say I think it's 11.4, and it's up there pretty high. I might even estimate the last number as being 8. Now, again, everybody in the world who's an engineer or a scientist, if they saw this, they would know exactly what my ruler looked like. They knew I had numbers for ones place, tenths place, and I had to guess hundredths place. And that's why you do it. Now, let's say you thought it was 11.5. I know you're going to like this. This right here would not be correct. This would not be correct. This would be correct.
We can't see what you're doing.
Oh. 11.5 would not be correct. You are misleading me. You're telling me you had a ruler where you had to guess tenths place. That's a lie.
Okay.
So that's why I know, here's the problem. If you're a science person, you know there's a difference between 11.5 and 11.50. There's a difference in that I know what instrument you used. You get it? It's communication. But if I put this in a calculator, I promise you there's no difference. Mathematics, math class, does not use measured numbers. Scientists and engineers use measured numbers. They have a set of rules that go along with measured numbers. A set of measured numbers said, if you put 11.50, I know what your ruler looked like. Do not tell me 11.5 because you're lying to me. So now you finally know, well, 11.50 is different than 11.5. Don't try to talk to your math teacher about this because they don't use measured numbers. What do they use? What?
What they know?
They do not use measured numbers.
No.
Whole numbers.
They use perfect numbers.
Computer saying-
If I tell you I measured something, it was 5 centimeters in here, I might be lying to you, not because I wanted to lie, but if you gave me a better instrument, a more expensive ruler, it might be 4.98. But in math class, 5 in math class is 5.00000 to infinity. It's the perfect number 5. It's not measured. It's not measured. Everybody look at me, okay? I'm going to see if you can understand that. Does that make sense to you?
Yeah.
Your math teacher would not understand this. They'll just say, don't write 11.50. It's the same thing. In the world of perfect numbers, it is. But not in the world of measured numbers. Not in the world of engineering. Not in the world of science. remember every measurement has what? A number. That's the right number of sig figs. A unit. And has what?
Unit.
Error. There's no error in math numbers. There's no error. They're not measured numbers. So what I'm going to show you is, and this, let's take a look here. let me demagnify. Whoa, look at that thing. Okay, now, if you have an older brother or sister and they went to school and they were a science person or they became a doctor, they'll probably remember the lesson they had on significant digits. They'll tell you that they hated that lesson because, and you're not going to hate it, because some teachers teach 6 different rules about whether a number is significant or not. Some books have 5. What I did is I crossed out all the ones you don't need to know. And I used to teach it like everybody else did. No wonder they didn't like it. I'm going to teach you the simplest way of figuring out whether or not, and by the way, I didn't write units here, but I just imagine all these are measured numbers, okay? Imagine they're all measured numbers like grams or whatever. Let me tell you, how do you figure out how many significant figures are in a measured number? Are you ready? Rule number 1. If you're a measured number and I see a number that's not a 0, it's 1 through 9, you're in the club. You're in. You are significant. So watch. Take my pen. I'm going to underline this too because you're in the club, 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 you're in the club. Oh yeah, you're significant. Oh yes. Now what I'm doing is I'm doing step 1 for every one of those. What do you think? Is it possible that, isn't rule number 1 really simple? In a measured number, if you're not a 0, you're in. Number 2, another easy one. When you go to college, if you become a PhD doctor or something like that, don't use this. I made this up myself. I call it the Oreo cookie rule. The Oreo cookie rule says if you have a significant digit here and a significant digit here, and you're a 0 and you're caught in between, like the cream in an Oreo cookie, you're in. So if you're the cream in the Oreo cookie, you got a wafer cream, you're in. So what I'm looking for, it says zeros found between significant digits, you're in. Let's go find some cream. Ready?
Yeah.
No, I only had one. I only have one wafer. I only have one wafer here. Those zeros, I don't know about them. How about, no, I only have one wafer. Oh, I'm going to put 2 lines here. Rule number 2 says you are an Oreo 0. You're in. How about this guy?
He's in.
Oh, yeah. One wafer. Only one wafer. Next. One wafer. One wafer. Oh, yeah. Triple stuff. Triple stuff Oreo. Triple stuff Oreo. Okay. Now, rule number 1, easy. Rule number 2, I think I can remember that. Rule number 3 is the only one. You got to give me a little bit of your effort, okay? Number 2, if I'm a 0 trapped between 2 significant digits, I'm in. I'm in the club. Now, rule number 3. Okay, I only got 1 minute. Ready? Watch. Trailing zeros. Trailing means I trail a significant digit. I didn't say trail a decimal. Don't do that. If you trail, that means you come after a significant digit. You're in the club if there's a decimal somewhere in that number. Now, do you see any zeros trailing the 2?
Nope.
I am done. I don't want you to learn the rules that tell you that these are not significant. Just learn the rules that say when they are. I don't have any trailing zeros. I did rule 1, 2, 3. I'm done. How many total significant figures I have? Oh, dang it. I kept looking at the 2. Sorry. Look at the next one now. Are there any trailing zeros there? Well, wait. Wait. Trailing zeros don't always count. Trailing zeros count if there's a decimal. Oh, I see a decimal. So you are in by rule number 3. That means there are 2 sig figs here. This one, I'm already done, aren't I?
Yeah.
There's 3 here. And what about this? Oh, I see a that's 0. Wait.
4.
Wait. I didn't say trailing a decimal. I said trailing a sig fig. It does.
Oh.
It does trail the 1, doesn't it? Is there a decimal?
Yes.
Then you're in.
You're
All right, next one. Watch now. I see a trailing zero,
One.
but I don't see a decimal.
One.
You know, scientist doesn't want to be confusing. So I didn't want you to say, oh, I wonder if he forgot to put a decimal here and these really count. Does he really have a really good instrument or not? And he's not going to do that. He or she's going to do this. See that? I'm going to put it in scientific notation. How many sig figs does that have? I'm telling you, I didn't have a great instrument. Now that, what did the instrument look like? Well, it went from 0 to 10 and 10,000, 1 0 to 10,000, and it was here. Oh, 5,000? That's not a very good instrument, is it? Let's go down here. Look at this one. What do you think? They're trailing, and I see a decimal. You're in. And again, if I was a scientist, what would I write? Aha! I'd write like that because then you'd be sure. You would be certain. You would be certain that it was significant, wouldn't it? 5.000 times 10 to the third? There's no doubt. How many sig figs does this have?
I don't know.
Are these trailing zeros?
Yeah.
Is she a decimal? Okay, how about the next one? Are these trailing zeros? Do they come after the 1?
2, 3,
I see a decimal? Yes. How many?
6.
All right, 6. And how about this one?
Um,
Why are you looking at these over here? They're not trailing. That's on 1, yep. How about this one?
5.
1, 2, 4.
Four.
Why do you think, tell me what rule makes this one significant? There is none. There is none.
There's none.
How about this? Oh, we're already done anyway.
1.
What?
5.
Okay. All right, thank you very much. And again, if you want to go home, some of the homework questions on scientific notation, significant figures, you could do those. You can knock those out really, really fast.